Hello everyone, Mr. John here for Airteam Institute's Introduction to Algorithms course. In this video we're going to be talking about computers and algorithms, just to give a little bit of an introduction to what these are as concepts and how we can kind of think about them and view them as far as this course is concerned. So, basic question at the beginning here, what is a computer? So we oftentimes have a pretty narrow vision of what a computer is. You're probably watching this video on a computer, or really I should say, you are watching this video on a computer. Whether it's a desktop computer, laptop computer, your iPad, your phone, whatever it is, we want to consider all of those different things computers. Actually, right, we can give almost a circular definition, but right, a very basic definition of a computer here is going to be something that computes. So what do we kind of mean by something that computes? You might say, how can you define computer in terms of computes, right? That kind of is cheating. That's not fair to do it that way. Well, right, compute just means something like it's doing a calculation, it's doing a task, maybe it's recording information, different things like that as well. The other thing I want to stress here, and this is going to be something we kind of come back to a lot in this Introduction to Algorithms course, we'll see it a little bit later in this video even when we start talking about algorithms, right? We generally think of a computer as electronic, but you could have a physical computer, you could have a biological computer, all of these different things are possible. So of course, we're gonna pretty much be working on the usual version of computer, right? You turn it on, it's electronic, we're used to those, our phones, tablets, laptops, all are more standard computers. That's of course what we're gonna be using more in this class. But we wanna just think of the definition as being more general. We wanna think of a lot of different possibilities as what this kind of computer could mean moving forward. Right, so doing the history of computing a little bit, this is going to go back to some of this stuff we talked about in terms of physical, biological, right, electronic. We're not really going to see too many biological computers here, but they do exist. But right, the history really starts with the physical, or maybe even you could say the theoretical. Right, so Charles Babbage was this mathematician, engineer, inventor, right? Back in those days, a lot of people did a lot of different things at once. He's often referred to as the father of computers because of this thing that's called the difference engine. Now, one of the famous women mathematicians, right? So if you haven't heard of this woman before, this is a great name to know. She's a pretty cool kind of person, especially if you're interested in computer science. Ada Lovelace, she did a lot of the work with Charles Babbage. So it's a little bit unfair to just call Charles Babbage the father of computers. Ada Lovelace did a lot of things with Charles Babbage as well. And this was kind of these plans for a computer, right? Here, literally computing, right? So the function of this machine was to compute values of different polynomial functions. You would, in a sense, input the polynomial, and then, right, the output would be different values of things like that there. Why am I doing kind of input in quotes, right? We're going to talk about those types of things too more in this course, but if this was a physical machine, that meant you're kind of physically inputting things. So these things had sliders, right? Different things like that as well. Now, other thing I want to quickly mention here that's kind of interesting, he never actually built this thing as far as I'm aware, right? He had the plans for it, right? The schematics, it wasn't built to a little bit later. But still, the idea, those plans encapsulated what we often think of as the goal of a computer, right? Doing one of these tasks and kind of doing it in a systematic, programmatic way as well. So where did a lot of this stuff then kind of really start shooting off, right? We'll see some exponential type stuff. When we study algorithms more, we'll talk a lot about exponential growth, right? And this really kind of started in kind of the 19th and 20th centuries, especially when people were talking about different military aspects. And a lot of this stuff is kind of a little bit fun in that it was like spy related, right? All your kind of famous thriller movies, right? They're doing codes and different things like that. One of the famous ones is this Enigma machine in the kind of World War II era, especially, right? These were things, again, if you have more and more complicated codes, more and more complicated encrypted messages, they get more and more complicated to calculate and encode or decode. So there were a lot of machines that could help out with this. This is one of the most famous ones because kind of it was powerful. It was what the kind of Germany used, right? The Nazis in World War II, and kind of the Allies stole some of those. And there's a lot of interesting history behind that I would recommend you look into if you're curious about, you know, spies at all, about cryptography at all. This is kind of a cool thing to do some more research from there. And as these things got more and more sophisticated, right? This is what you would say, right? You might know the word arms race. There was really a computing arms race going on at the same time. These first digital electronic computers were happening during those same times in World War II's. They were huge. I mean, literally huge, taking up full rooms, things like that, right? You had vacuum tubes, all kinds of different things. So these were huge physical machines. They were electronic, So these were the first things, if you think about how a modern computer works with, the different signals, binary stuff, these were the first types of things that really worked under that same structure and have, of course, gotten smaller and smaller and smaller since, right? I'm pretty confident saying that my phone right here has more powerful than the machine you're seeing in that picture there as well, right? So what used to take up a full room is now tiny, tiny, tiny that way too. This brings us to one of these famous laws, right? Of course, it's not a legislative law that Congress passed or something, but right, Gordon Moore did this Moore's law, guessing or predicting that kind of performance would double roughly every 18 months. He said kind of a year or two, and just kind of this performance exponential growth. We have kind of a logarithmic scale here. That's why it looks linear, right? But notice that here on the side here, we're growing, right? Not in a linear fashion. So that is where we're kind of getting a linear scale seemingly in the picture, but it's really kind of exponential growth that way as well. And so one of the things, right, that this is kind of telling us is that, especially if we're talking theoretically, right, things are going to get faster over time. And so when we start talking in future videos about algorithms and how efficient algorithms are, stuff like that, this is one of those things that we need to keep in mind, because computation will be getting faster. A lot of people have been saying for years now that this is not sustainable. A lot of people are also saying, we know we've been saying that for years now, but we really mean it now, because as things are getting really, really tiny, right, all your little processors, right, the little circuits involved, they're getting so small now, they're actually running into issues with quantum mechanics, and kind of you're dealing with real thermodynamic problems at such a small scale. You're trying to do things so quickly, they're generating a lot of heat, and so there's all kinds of complicated things going on there. But we'll have to see if we're at the end of Moore's law, or if that other things kind of will really break through and kind of change that as well. Real quickly, a little bit of an aside, but we also are possibly at a point in history where Moore's law is going to kind of break completely in terms of quantum computers. So if you've heard about quantum computers before, right, or things like that, I'm not going to do too many details here, but in a way that would kind of just break all of this stuff. That's a whole different model of computation. They deal with things totally differently. And so that would be kind of just a whole huge shift in all of the computation stuff that has been going on in the past decades. So still, right, I might have to change this in a few years, but what is the most powerful computer still? So this is really a little bit of an abstract question, right? What do we mean by powerful in this case? But right, by many accounts, by most accounts, right, still the human brain is the most powerful computer in the world, right? So these are kind of still probably more powerful than the best supercomputer, right? But this could be changing pretty quickly. So a lot of estimates, at least this century, so sometime in the 2000s, computers will pass the power of the brain. And so some interesting things could be happening there, but those kind of shift pretty quickly into theoretical questions, philosophical questions that we don't need to get into for now. So what is a computer? We want to take a more broad idea of that as well. What is an algorithm? Similarly, we are going to focus on some details, right? We are going to talk about programming a little bit in this course, but we also want to at least have in our mind a wide view of what's going on as well, right? So at its core, an algorithm is a step-by-step set of rules or operations describing how to complete a process. Oftentimes, when you say an algorithm, you're going to be talking about a specific problem that you want to solve. That doesn't need to be the case, right? But it's often easier to think of it that way. So again, stressing that these things don't have to specifically be computation, right, in the strict sense. They don't have to be kind of computer related in the strict sense, right? For example, long division, right? Probably if I ask you, do you know an algorithm for long division? You might say no, right? Well, you actually do in, right, third grade, fourth grade, second grade, whenever you learned it, right? You wrote out the numbers, you kind of wrote one number here, you said, okay, how many times does it go in? We subtract, blah, blah, blah. That's an algorithm. We don't think of that as a kind of standard algorithm, or you may not think of it as an algorithm, because you say it's something that you do on paper or things like that. That's fine. That's still an algorithm. You could talk about it in many of these same ways, right? Euclidean algorithm is maybe something you're familiar with. That's a more common algorithm, right? We'll see implementations of that at different times in this class later on as well, right? That's something you program and can practice your programming by calculating that algorithm, right? To calculate the GCD or GCF of two numbers. But again, other things like how do you solve a Rubik's Cube, right? Algorithms exist. If this is what the Rubik's Cube looks like, you do these motions, right? It's a systematic step-by-step set of procedures that allows you to solve a problem, right? Here, put all the kind of manipulate the cube so that all the faces have the same color, right? That is your goal. That is what the algorithm systematically allows you to do along the way. Okay, so as one example here, this is where we'll kind of practice a little bit with what we want to talk about in terms of an algorithm. Let's answer a very, very simple question of, is it even, right? So what is a method? What is an algorithm for testing whether a number is even? There's a lot of different things that kind of go into this as well, right? So a lot of you probably think about a very, very simple algorithm, or you think of a very, very simple kind of procedure you might do here. So for example, one common way you might do this, right? You might say, look at the last digit. Look at the last digit. If it is 2, 4, 6, 8, or 0, the number is even. So this, right, is an algorithm. This is a procedure. You could do this as a person. So again, it doesn't need to necessarily be done on a computer, but it is good to clarify who the algorithm is for, right? So this algorithm, right, is probably fine if we're talking about a human, right? A human can probably run this algorithm. A human should be able to run this algorithm, right? Maybe let me put run in quotes, right? I mean, you read that, then if I give you a number, you can interpret my instructions to you and kind of understand how that's kind of happening and what is being done as far as that algorithm is concerned, right? So you can kind of run that algorithm. Could we make a computer run that algorithm? Sure, we might still have to think about other things. How are we giving it the number, right? Does it know it's a number? Does it have to kind of use imaging or something to try to read the number, right? These things can get pretty complicated. A lot of the times we won't worry about those details, but we want to at least keep them in mind as something you want to be conscious of when you're doing these things, right? You could do some stuff, right, to extract the last digit of the number and then see if it's even, stuff like that as well, right? So if we just look at maybe one other example at least, right? So some of you might think about remainders, right? So to divide the number by 2, right, and see if it has a remainder of 1 or 0, right? If it has a remainder of 0, it is even. Right? And so this is another good example in terms of knowing who the algorithm is for. So in a lot of ways, this algorithm is more complicated, right? If you were just telling another person, if you're explaining, if someone had never heard of an even number before and you wanted to kind of explain it, tell them how they found even numbers, there's no debating, I think, that 1 is the easiest thing, right? You just could even give them pictures. Look at these numbers, 0, 2, 4, 6, 8, right? Those are what those numbers look at. Look at your number, go to the end. If you see one of these numbers on the card I gave you, the number's even, right? So someone even probably who didn't understand English or didn't understand our number system or something, they could still follow that procedure to know even or odd. Even if 2 is more complicated, right? This remainder stuff is something that computers can do very well, right? So computers do this very well, and this is a quick way to write a program to test for even numbers, right? So this video isn't focused on, specific languages. We are going to be doing a lot of Python in this course, but I also just want to stress that all the different languages are very similar, right? So these remainders or mods in a lot of programming languages are a command you can type in. So test if the number has a remainder of 0 or 1 when you divide by 2. If it's 0, the number is even, you're done. So those are good things that kind of can be kept in mind. We want to think what's the kind of point of the algorithm, who's it for, and different things like that too. In the next video, we're going to talk a little bit more then about algorithms and stuff as well, right? Some of the things we can do there, we can be talking about implementations of them, and in the future, we'll also talk about what makes a good or better algorithm than other things too. That, however, is the end of this video. So Mr. John here saying goodbye. Thanks for watching and hope to see you guys all soon.